welcome to RF transceiver design course. We are discussing about the phase noise. So, while discussing the phase noise, we have discussed that what is a unit that is widely used in the in order to find the phase noise, that is the dBc per hertz. So, if we want to understand the phase noise, we again will come to the one port view of the oscillator. Now, in one port view, what we already have studied, that there is a RLC resonator. So, this is RLC resonator, and we required a active component which generate the negative resistance. So, if we try to consider the noiseless magic box, means there is a no noise generated, and we take a noise out which is given by the, if we try to draw it, this is an inductor, then there is a capacitor, and resistor. You will have a noise which we have taken out, noise current I n square by delta f. So, this is noise current density, and then we consider this as a noiseless box. Now, we will try to find out the noise. This is given by lessons, means the scientist lessons has derived this model of noise, phase noise. We will get at a small frequency of offset delta omega, at small frequency offset delta omega for LC tank. We can write a y omega naught plus delta omega, which is equal to G if we consider the transconductance G, plus J omega naught plus delta omega C plus 1 by J omega naught plus delta omega L. So, if we try to multiply this on this side, you will get equivalent y, which is G plus J 2 omega naught delta omega divided by omega naught plus delta omega into C. So, the y you can convert into the z. So, we will see on other slide. So, z, which is equal to omega naught plus delta omega, equal to 1 by we can write 1 by G 1 by 1 plus J 2 omega naught delta omega by omega naught plus delta omega into R C. So, your Q, which is equal to omega naught R C, you can write Z omega naught plus delta omega equal to R, 1 by G is equal to R into 1 by 1 plus J omega naught R C is given by 2 Q delta omega by omega naught plus delta omega. So, if we consider the real part of this, is if we consider the magnitude which is given by, this will go up r omega naught by 2q delta omega. So, this is a impedance that we have find out, that is r omega naught by 2q delta omega. If in this term omega naught plus delta omega, omega naught is higher. So, we can write a noise power spectral density with delta f equal to in square by delta f z square. So, the voltage can be given by this. So, this can be written as a 4 kT G, because we have considered the transconductance current, into r square, this r square omega naught square by 2q delta omega. So, this both G and R will be cancelled out. We can write a 4 kT, 4 means one of the R and G is cancelled out, 4 kT R omega naught square by 2q. So, this is also whole square, 2q delta omega square. Now, what is happening, that there is a possibility that your noise phase, what we have considered the complete noise. So, noise can be divided in terms of amplitude and phase. So, if half of the portion of this noise is contributed towards the phase, then we take the half of this, and that we will get a phase component. So, phase component is given by, so your phase component is equal to 2 kT r omega naught by 2q delta omega whole square. So, based on the lessons model L delta f delta omega, why we have considered delta omega? Because here in the phase noise we are interested for the delta omega offset, as I already discussed in the last class. So, L delta omega equal to, we can write 10 log of 2 kTr omega naught by 2 q delta omega square divided by the source noise, which is given by Vs square. And if we consider Vs square by R as a signal power, which can be written as a 10 log 10 2 kT by P signal omega naught by 2q delta omega whole square. So, this is how in this equation the only second order has been considered. So, if you see the, if you see this model of phase noise, then there is a this two portion, means this and this has been captured. So, 2 kT by P signal omega naught by 2q delta omega square. So, this third component is coming due to the flicker noise. So, this is happening because of the thermal noise. Now, due to the flicker noise in the device, this third 1 by f, because of 1 by f noise, this 3 times slope is coming, and that is that we need to add. So, in order to do that, here with this term 1 plus omega naught 2 q delta omega, one more term can be added, that is a 1 plus delta 1 by f cube by delta omega. So, this is a third order component, and this is f, which is a empirical parameter which is added in order to satisfy this. Otherwise, this green curve means the whatever we have find out, this is representing this green curve. So, in order to have this slope, this additional term has been added, and this empirical term f has been added, so that you will get the phase noise model which is accurate as we are getting in measurement. So, this is how the phase noise lessons model has been developed, and it is capturing all the components of the phase noise. If you are interested more of understanding on the same phase noise, there are various phase noise models are available in the literature. You can go through it. The fundamental important thing in the phase noise is it has a, in order to understand it as a the third order slope, second order slope, and the constant throughout the frequency as a thermal noise. So, at omega naught frequency up to the corner frequency of the MOSFET or BJT, any active components, it is going to have a third order slope. After that, up to omega naught by 2q, it is a second order, and then it is a constant. So, this is a model of phase noise, and which you can apply to any oscillator that we have already studied. You can go through the literature for more understanding on phase noise. So, in the lessons model that we have discussed, there is a some issues with the lessons model. So, we already have discussed that how this empirical term f came, and that f term is added due to the 1 by f noise. Now, this empirical term is not defined in the lessons model, and if we try to improve the phase noise, the improvement of phase noise is depend upon the quality factor q. So, if we increase the quality factor q, we can quality factor of the resonator, we can improve the phase noise. However, this if we try to improve the q with active components, and it might leads to increase in the f, which is the empirical term defined. So, this there are many places this model has a some invalid assumption, that is a f, and that will leads to designer to decide that what to change and how to improve the phase noise in the oscillator. So, we try to see another model of phase noise, another model how we can analyze the phase noise compared to this lessons model. So, in lessons model there is a linearity, means we have considered linear time invariant system, but in reality non-linearity is a fundamental property of real oscillator, because without non-linearity we cannot have a oscillation, and it is also necessary for amplitude limiting. Now, what will happen? This results in a single frequency sinusoidal disturbance injected into oscillator, and it will rise rise to two equal amplitude sidebands, and which are symmetrical above the carrier. So, linear time invariant system cannot perform a frequency translation, and that is why what we need to consider is a nonlinear system. We already have seen while discussing the RF mixer. So, nonlinear mixing has often been proposed to explain the phase noise. So, the important insight is that disturbance or perturbation superimposed on the main oscillator, and they will always be much smaller in magnitude than the carrier. And we are when we are doubling this disturbance, it is doubling the phase disturbance. So, it is like when we are considering the linear, means in terms of the phase noise. So, that phase disturbance is also increasing. So, it is following the superposition theorem, where addition means doubling the disturbance is also doubling the phase distribution. Linearity, therefore, we can consider, but we cannot consider time invariant system. So, for the model that we have discussed in the lessons model, that has considered the linear time invariant system, but we should consider the linear time variant model. So, we will discuss the linear time variant model. So, this is an example in which there is a inductor and capacitor which has infused the current IT. Now, if we have this impulse which is considered as a delta function t minus tau, and at what place we are adding this impulse function, it will change the either amplitude and phase accordingly. So, there are two possibility that this impulse is occurring at tau where the maximum amplitude is there, and it will increase the voltage amplitude by delta V. So, there is a change in the voltage amplitude delta V. However, if this impulse is happening at the zero crossing and at the this tau, then what will happen, it is contributing to the change in the phase. So, what is happening here, the amount of phase disturbance for a given injection pulse depends on when the injection occurs. So, here uh, time invariance thus fails to hold. So, what we need to consider is a linear time variant system. So, an oscillator is a linear yet a time varying system. It is varying with the time. Now, we will try to use the LTV model, means instead of LTI model, to define the phase noise. So, we have considered the linear model. So, linearity correspond to noise to phase conversion, and as noise is doubled, phase is also doubled. So, here LTI impulse response is a function of a two argument, that is the observation time t and at what time excitation is occurring, which is a tau. So, we can write a impulse response which is a hft comma tau, which is a function of t and tau, and it is a variable which is a gamma omega naught t. Now, what is this gamma? This gamma is nothing but a impulsive sensitive function. This is very important to understand for this LTV model. Now, what is this impulsive sensitive function? So, if we consider this is a unitless, and if we consider the LC oscillator, this impulse sensitive function can be written as a, it is a periodic in nature. It will change for LC oscillator like sinusoidal, and for ring oscillator it has a impulse behavior like this. Now, here uh, what is happening, that this function, impulse sensitive function, has a maximum value if for LC oscillator, maximum value near the zero crossing. So, at zero crossing it has a maximum value, you can see at this it has a maximum value, at zero crossing this it has a maximum value, and 0 value at the maxima of oscillation. So, it has a 0 value at maxima of oscillation, and this impulse sensitive function is divided with the maximum charge displacement across the capacitor, and this is a unit step function ut. So, this is how we can derive the impulse response, and it can be written in this form. It is divided by q max, so that it can be a unitless function. Now, what we will try to see that how this will be converted in terms of the phase change. So, when we try to find out the excess of the phase due to arbitrary noise signal through the superposition integral. So, here the same integral, whatever is this equation which is written here, this is a uh, this is flow chart or block diagram. This is a block diagram of the same equation. So, IT by Q max is a input, gamma omega naught t, which is a impulse sensitive function, is input, which will generate the function xi t, which is this, and when there is a integration over the time, it will provide you the phase phi. Now, this phase will be converted to the voltage. So, you need to convert a phase to voltage conversion with a phase modulation, and finally, you will get the output voltage V t. So, we can write a phi t, which is a output integration minus infinity to infinity h into I tau d tau. Now, we already know this function h phi t comma tau. We write 1 by q max, maximum charge, minus infinity to t. It is a function of gamma omega naught t, impulse sensitive function, into I tau d tau. So, this is a phi t which is in relation with the impulse sensitive function gamma omega naught t. Now, this gamma omega naught t is a periodic in nature. So, because it is a periodic in nature, we can decompose into the Fourier series. So, this gamma omega naught t we can write in terms of C naught by 2 and Cn. So, this is a DC quantity, Cn cos n omega naught tau plus theta n. With this will change. So, it has a multiple coefficient C0, C1, Cn, and it has a frequency component which is given by cos omega naught tau plus theta. So, same block diagram can be redrawn, and where each impulse function with the each sinusoid can be added, and this is the final addition, and we will get the phi t, and this phi is converted to the voltage. So, when we put this in this equation, we will get a phi t, which is 1 by q max C naught by 2, same thing, minus infinity tau I tau d tau plus this function. Now, what is happening, this phi we need to convert into the voltage. So, we have considered this. Now, we will apply the current IT, a sinusoidal current IT, which is IT equal to Im cos m omega naught plus the delta omega t, and where delta omega is much less than omega naught. So, phi t can be written as Im Cm sin delta omega t by 2q max delta omega. So, now we came to the function phi t, which is a phase, and that phase we need to convert into the voltage. So, the output voltage VOT, which is given as a cos omega naught t plus phi t. So, this is a output voltage, and where phi t is given by this equation. Now, performing this phase to voltage conversion, and if we assume a small amplitude disturbance, we find that a singleton injection results in a two equal power side bands. So, we already know that we have a two side bands, one is on this side, one is on this side, and this is a center. So, this will have a delta omega distance, and we can write the equal power side band, and that is also divided in, if this is amplitude, that will be divided in a half half. So, we can write a power spectral density for delta omega, which is equal to 10 log of sim IMCM by, because it is divided by 2, 4 q max delta omega whole square. Now, this result may be extended to general case of a white noise source. So, here we can use this white noise source IN square by delta f, and then instead of considering the Cm, we consider the all terms of Cm, m is equal to 0 to infinity Cm square, and this is a 4 q max, because now this is also power quantity, this is also power quantity, and this square term is coming here. So, 4 q max square by delta omega square. So, this is a delta omega, whatever is the noise which is coming back to the 0 frequency. Now, we will try to analyze how this is coming. So, what is happening? This is a thermal noise. So, this is a thermal noise, and this delta omega is distributed over a omega naught, 2 omega naught, 3 omega naught, and up to n omega naught, and all these with with a component multiple, this all multiple component with this coefficient C naught, C1, C2, 3, C2 or Cn, it is multiplied and it is coming to the 0 at the frequency 0. Now, what is happening, that this all, and the 1 by f noise, that is this is In square by delta f noise, and that 1 by f noise is also uh, contributing at the 0 frequency. Now, what is happening, that due to the phase modulation, whatever is coming at a 0 will be up converted to the omega naught frequency. So, because LC tank, it will act as a filter and it will tune only at one frequency. So, all this noise component, and which is a down converted with the different amplitude C0, C1, C2 and C3, it will be up converted to the omega naught by phase modulation. So, these components of noise near integer multiples of the carrier frequency all fold into noise near the carrier itself, and it is clear from figure that minimizing the various coefficients Cn. So, if we try to minimize C0, C1, C2, C3, we will minimize the phase noise. So, this phase noise, now what will happen, what happened in the lessons model, we do not have any concrete proof and concrete method to reduce the phase noise. Now, because of this we got the because of this impulse sensitive function, we come to know that we can reduce the phase noise if we can reduce this coefficient C0 to Cn. And if we use the Parseval theorem, this is nothing but a RMS value. This all summation can be derived in terms of RMS value, which is a 2 gamma RMS square, and that if we replace in that equation the spectrum of 1 by f square region, then can be expressed by this equation In square by delta f gamma RMS square by 2 q mx square into delta omega square. So, this is the same equation. Now, this has been replaced with the 2 gamma RMS square, and that 2 will be cancelled with the, and we get a 2. So, now this model will help us to understand there is no any empirical term, all are a defined term, and we can have a we can handle the phase noise. Now, this up conversion of 1 by f noise into uh, close in phase noise, that I already told, and noise near the carrier is particularly important in communication system with very narrow channel spacing, and the allowable channel spacing are frequently constrained by the achievable phase noise. However, unfortunately, it is impossible to predict a close in phase noise correctly with the LTI model, and this problem now is disappear if the new model is used, and specifically assume that the current noise behave as a follow. So, 1 by f region we can write in square 1 by f is equal to n square 1 omega 1 by f by delta omega, and if we put this in that equation, 1 by f is a 1 by f corner frequency, and we obtain the following expression for the noise in the 1 by f cube region. So, L delta omega we can write equal to 10 log I n square by delta f c naught square 8 q max square delta omega square, and this is omega 1 by f by delta omega. So, this will be replaced with this equation. So, the 1 by f corner frequency we can write by using this equation, that delta omega 1 by f cube is equal to omega 1 by f into c naught square. So, this is c naught square by 4 gamma RMS square. So, this is we have considered the same c naught square by gamma RMS square. This when we write this delta omega 1 by f3. So, this will have a this term is in denominator 4 gamma, and c naught square is nothing but the DC quantity. So, that can be written as a omega 1 by f gamma DC by gamma RMS whole square, because c naught square we can directly write this to gamma RMS square. So, that can be written as a gamma DC by gamma RMS whole square, and this will provide the insight into how you can. So, what is the corner frequency? So, if this is a phase noise, so that 1 by f corner frequency. Now, this corner frequency does not mean to be same as a, means corner frequency after the oscillator corner frequency does not be a same as a frequency of the circuit or the device. So, the corner frequency of the oscillator does not same, uh, it need not to be same as a 1 by f noise corner frequency of the circuit and device. So, that can be reduced, means that we can improve the 1 by f noise corner frequency by reducing the gamma DC component of the impulse sensitive function, and we can improve the phase noise of the oscillator. So, this model is this is a linear time variant model, and this model helps us to understand the phase noise, how we can improve the phase noise by various method, and in order to understand the phase noise we should have a understanding of this impulse sensitive function, and which can be realized as a periodic in nature, and we can uh, try to reduce the phase noise by having the by reducing the DC term of the same. So, This is about the phase noise. We have discussed the two model, one is a linear time invariant model and linear time variant model. Now we will discuss one of the important effect of the phase noise, that is a reciprocal mixing. So what is happening in reciprocal mixing? Because up to now what happened, that while the down conversion we have considered that there is a only single tone which is appearing f naught. This is a desired LO frequency, but due to phase noise there are a the LO frequency looks like this, and at due to this noisy LO phase noise, due to this phase noise, there is another component which is at this place at some delta omega distance. Now if there is some unwanted signal or interferer is also at the frequency just of the IF frequency, desired IF frequency, then what will happen, that this LO and this unwanted signal will down convert to the baseband, because the IF frequency is remain same, and this is called a reciprocal mixing. Now this reciprocal mixing we can in order to avoid, we need to have a sufficient uh, improvement in the phase noise, means there should be a sufficient phase noise so that some unwanted signal amplitude will not down convert due to this phase noise. So that can be given by, so the maximum allowable phase noise when we are designing the oscillator, the maximum allowable phase noise in order to achieve an adjacent channel rejection for a or a selectivity of S dB, we can write a, this is a equation. So where L is a phase noise equal to C dBm minus S, that is a rejection, and I is the interference, and then this is the bandwidth. This will be defined as a dBc per hertz. Now we will take one example so that we can understand. So in this example, the GSM cellular telephone as a standard requires a minimum of 9 dB of rejection of interfering signal level of minus 23 dBm at 23 megahertz. So what we want is a rejection of 9 dB, minimum 9 dB rejection. So this is nothing but a S in that equation. An interfering signal level has an amplitude of minus 23. So this is nothing but I at 3 megahertz from the carrier, minus 33 dBm at 1.6 megahertz. So if you consider this, and then there is a at 3 megahertz it has a minus 23. So this 3 megahertz has a minus 23, then 1.6 megahertz has little bit low amplitude, that is minus 33, and minus 43 dBm of interference at 0.6 megahertz. So for a carrier level of minus 99 dBm. So this is a carrier level which is minus 99 dBm. So what we need to determine, the required LO local oscillator phase noise at this carrier frequency offsets, and the channel bandwidth is given as a 200 kilohertz, because bandwidth is also important here. If a bandwidth is more, then this phase noise will also be phase noise improvement is also required more. So this LFM is derived. So we can consider that for 3 megahertz offset it should have a minus 138 dBc per hertz, and interfering signal level is minus 23. For 1.6 megahertz offset, it has a interference signal is minus 33 dBm, and phase noise requirement is minus 128. So you can see that as we are near to the carrier frequency, the phase noise requirement is little bit relaxed, and the interfering signal level, which is a smaller compared to the interfering signal level which is a at center frequency. So if you have at zero point 0.6 megahertz, the interfering signal is minus 43 dBm, you need to have at least minus 1110 dBc per hertz at the offset frequency of zero point 0.6 megahertz. So this is how we can identify the phase noise in the oscillator for reducing the reciprocal mixing. We have discussed about the oscillator and phase noise. If you are interested to have a more in detail understanding, you can refer this reference, and it will help you to understand in more detail. All this material has been considered from these references. Thank you.